All right, hello everyone. This is section 5.5. Um, this is a really cool, actually, section, I believe. It's one of my favorites, actually. It's a pretty cool application of the derivative. And the whole basic idea in this section is we're going to use tangent lines, which we know are derivatives, to approximate functions and things like that. So the first, and the book does this in a really, really weird way. So I am going to try to make it more clear. If you're just reading the book, you might have some trouble with this. So we're doing what's called local linearization. So you're going to hear this term where they just say use local linearization or find the local linearization of. When you hear the term, actually when you hear any of these terms today, they all refer to tangent line. So if you just think that, it actually simplifies things a little bit. We've done some tangent line stuff before. I'm going to go through this fast because I'm just going to basically tell you we're just trying to find a tangent line right now. So the idea is this, before we get into it. If you think about a curve, so here I have this curve that I'm drawing in red. If that curve is a complicated curve, like it's got a complicated equation, it's got lots of trig functions or square roots or squares or things like that, what we're going to do is we're going to use the idea of the tangent line. If you notice this tangent line I have drawn there, as long as I'm pretty close to this point A, my tangent line is pretty close to the curve. Okay, it's true of any curve, any point, anywhere, that as long as you stay close to the point of tangency, the tangent line stays pretty close to the curve. So what that means is we can use the tangent line to approximate the curve. It's a lot easier to plug something into a linear function than it is a quadratic function with trig things in it or something like that. Keep in mind this was all done before calculators. I know we have calculators now, which solves a lot of these issues. We're not using calculators in this because calculators can do it. We're just going to use these approximations. So local linearization is this. So this is what's called local linearization. It's simply f of a plus f prime of a times x minus a. You can memorize that. But notice this is really just a tangent line, because if I write a tangent line like y minus y1 equals m times x minus x1, now we just call that an a instead. Now it becomes y minus f of a equals m times x minus a. That m is just derivative, which is f prime of a. And then if I bring it over to the other side, y equals f of a plus f prime of a. You see, it's the same thing. So the format doesn't really matter. Just when someone says find the local linearization, they're saying find the equation of the tangent line. Okay? Hopefully that makes sense. So the whole idea is, again, it uses the tangent line to approximate values close to A. You got to still stay close to that point of tangency. Otherwise, we don't know what's going to happen, right? So a little example problem would be, let's just do one. And remember, and sometimes I take the word local off, by the way. So you might just hear find the linearization. So again, just remember all this is asking us to do is find a tangent line. So I'm going to go through this relatively quickly. My first step is to find that tangent line. So notice, or find the tangent. It's just a power rule. So the derivative is 1/2 times 1 plus x to the negative 1/2. We're trying to find it at 0. So now I plug 0 into this, and I get 1/2. So now notice I have the slope, which is the slope of that tangent line, and I have a point. Well, I don't have the point yet. I guess I'll put in 0. If I put in 0 for x, I get 1 for y, right? So now I write it as local linearization. It's f of a plus 1/2, which is that slope, times x minus a, or again, it looks like this, right? So I'm just going to rewrite it like I would if it was a tangent line, because it can get messy, right? It's just y minus 1 equals 1/2 times x minus 0. That's all it is. This is going to look a little funnier because of their order. And then they just bring this to the other side, 1 plus 1/2 times x minus 0. And then if you want to simplify, it's 1 plus 1/2 x. So this idea of the tangent line is really, really quite powerful, actually, in terms of approximating. So again, remember, if we stay close to that point of tangency, the purple line on that picture there is close to the red curve. Okay? So that being said now, we're going to take this idea and extend it to this thing called differentials. Differentials, tangent line also, just so you know, it's the same thing, but we're going to shortcut it so you don't have to do that process. If you like that process of tangent line, I'm going to show you how to do this problem two different ways, so it works the same. But differentials is very simple. dy equals f prime of x. So if you start with y equals f of x, the idea of differential, dy means change in y, and dx means change in x. This is actually approximate change in y. It's just an approximation, right? So first things first, I'll just have you find a differential, but then I'll show how we can use it in real equations, okay? Finding the differential is very simple. If we have a function and we want to find the differential, what we do is we go dy is, we just take the derivative, right? Derivative, and multiply it by dx. So we get 9x squared plus 4x minus 1 dx. Now here's where this becomes powerful. If I wanted to, let's say, let's find a nice easy point for us right now. How about we put in just 0? Let's just put in 1. So if we put a point into this equation, we put in 1, we get 3 plus 2 is 5, minus 1 is 4, plus 1 is 5. So we have this point 1, 5. So if I were to draw a picture of this curve, I don't know what it does. It's some sort of cubic. It's a bad picture. Let me try that again, just to make it look sort of right. It's got up here at the 0.15. It's some sort of cubic. I don't know. We'll just say it does this. So let's say I wanted to approximate this function at 1.1. All right. Well, it'd be a little bit annoying without a calculator. So remember, I don't have a calculator. I don't really want to put 1.1 into that and cube it and square it. It's kind of annoying. And if those are even harder, then it's even more of a pain. But the idea is this, same thing as tangent line, that I could just put 1.1 into the tangent line, and I know I'm going to be pretty darn close, okay? So as long as I'm close to that point of tangency, which 1.1 is, if I was at 2.1, probably wouldn't work. So we can just plug that in. So what we're going to do is this. We're going to go dy equals. Now we're going to plug the x is 1. So we're going to plug x as 1 of this. So it's 9 plus 4 minus 1 times my dx, which is my change in x. So remember, x was 1. My dx is 0.1 because I was trying to find, really what I'm trying to find is 1.1 comma question mark. Okay. So my dx is 0.1. And now I can go 9 plus 4 is 13, minus 1 is 12, times 0.1 is 1.2. I'm out of space here. dy equals 1.2. So what that means is that's the change in y as x goes from 1 to 1.1. Right? So x is 1, y is 5, x is 1.1. Y has to be that 5 plus that 1.2, or 6.2. So that's my approximation for plugging 1.1 in there, as I get a 6.2. Now watch, the idea of differentials really oversimplifies that, so it's really cool. You can just plug it in those numbers, you have to do it. But I could just do tangent line. If that bothers you, or the first couple of times, it's going to feel weird for sure. But watch this. I can just take the same formula, same problem, and watch what I can do. I can find the equation of the tangent line. So at the point 1, 5, find the equation of the tangent line. Same point that we were given in the first place, right? So I go dy equals 9x squared plus 4x minus 1. Plug 1 into that. Sorry, this should just be y prime. Let me not use that same terminology because I'm not doing the differential. I'm doing y prime. So y prime equals 9 plus 4 is 13. It's 12. So my slope is 12. So my equation is y minus 5 equals 12 times x minus 1. Or y equals 5 plus 12 times x minus 1. All right. I'm going to try to pause this if I can figure out how. No. I'm just going to keep going and finish this real quick. I'm being interrupted here. That's why. So now I just plug in y equals 5 plus 12 times 1.1, because that's what I'm trying to find, right? The equation at 1.1, 5 plus 1.2 2, and there's my 6.2. So I'm going to stop there. There is one more equation, one more example that I'll do on a next video. Since I'm being interrupted here, I'll be back.